right, good morning. How you guys doing? See one yawn, ready for a nap, right? Okay. I wanted to give you a couple quick updates. I made a quick update to the syllabus. I have not posted it yet, so I need to do that. Today we'll be talking about some of a little more solubility, precipitation reactions, and a bit of water softening, kind of touch on that. We've talked a lot about the core components that go into how we soften water with a chemical approach. So I wanted to tie a few of those things together, kind of tie our discussions about carbon dioxide, a carbonate system together to look at solubility. So we'll do that. Next time I actually need to update this a tiny bit more again. Well, first of all, next time we have a Flint water crisis, I've given you instructions on that. So go back to see that email and see the resources I posted for that. And then I will probably also post a couple articles I forgot to post. So I'll probably post a couple articles for you to read a little bit further for your curiosity. Kind of just skim these articles to see really the aqueous chemistry principles at play in them. Then I decided I wanted to cover redox chemistry as one of the core pieces before we get to exam 2. So we'll have some of that with the lectures next week, have exam review, and then I'm going to do some aqueous photochemistry, which will tie a little bit into my research as kind of an add-on that we're not going to be tested on. So that's kind of the plan at the moment. I did post your second homework assignment. That'll be due on the 19th. Here, double check that I think maybe I put that in on the 21st, but it should be the 19th. So I might need to go edit that. But we'll cover the solutions on the 19th, so it will be due that day. In addition, I will post kind of the next step for our larger project, and I will give you more instructions on that larger project. My plan is to kind of solidify that, what I want from that, and then within the next week. So I hope to give you some more guidance and at least the next step towards that before next Tuesday. Okay, so that's a little bit about kind of where we are, what we're going to talk about today. Any questions or concerns about all that? Okay.
So when will the project be?
The project will be due on the date of the final exam, but we don't have an exam, so the project is in place of it.
We won't have the exam, we'll have the project,
right? Right. Yeah, so I might ask you to give a small presentation or something like that as part of it. I'm gonna hold that final exam slot. Kind of reserve that in case I decide that's what I want to do. That or the last class period of our class. But more on that specifically next week when I sort out my details. Okay. Any other questions on that? Good. Okay. All right. So we left off last time talking about this stannous fluoride, tin fluoride chemical. We looked at this example. We said we'd pick up here next time and kind of look through the solutions together. So here we have SnF2 added to pure water, and we were tasked with, first of all, if we are given some data that 12 milligrams of this stuff dissolves in 100 milliliters, determine the solubility product. So that's something we can do, knowing that our solubility product is going to be equal to the. We can solve using the activity, and we can do all those corrections, and the book will mention that, but I'm not going to trouble us with that at the moment. So if we have 10 here multiplied by the F minus, we have to square this term because we know that what look like as a dissolution will be with 1, 10, and 2 F minus, right? So the 2 there means we need to square that when we do the solubility product. So given that, and we know exactly how much dissolves, that's going to be at our saturation point. So we could solve for this amount of tin, this amount of fluoride, and come up with our part A. Part B then says, okay, so what is the solubility of this mineral if we have a solution that originally contains 0.8 moles per liter of sodium fluoride? So giving us 0.8 moles per liter of F minus, which given this circumstance, we could then solve for, okay, well, how much of the tin is going to dissolve given that we know this and we know this? Our equilibrium is going to shift such that not a lot of tin is going to dissolve. It's kind of the expectation. So that's the process here. So we'll kind of take a look here. So first, we convert from mass to moles, get that into this 12 milligrams, turns out to be 7.66 times 10 to the minus fifth moles. That's per 100 milliliters, so we can get that to moles per liter by dividing by 0.1. Okay, so that's 7.66 times 10 to the minus fourth moles per liter. For each tin, there's 2 fluorides. We talked about that. So we can find those 2 concentrations, plug them into our equation for K, and get a value there at 1.8 times 10 to the minus 9th for the solubility product. So that's part A. And we can go ahead and highlight that as the answer. So part B then, we say we have to go and then find this solution. Or did I jump ahead of myself? Maybe I think that was it. Okay, I just repeated it, sorry. Okay, so just a little redundant here. So part B, we're going on to say, okay, well, we've added a whole bunch of this other stuff, this sodium fluoride, to it, so we have a bunch of fluoride. Now, there's also a note here saying we calculated the concentration-based solubility product. There's a little C there. I haven't really highlighted this too much whenever we've encountered it in the book, but this is just meaning we used moles per liter, but we maybe ought to or could use activity, which would put a little A there. So you can say concentration versus activity. So we could make that correction, and if we're going to be very particular, that would be good, especially in the second case. But for the sake of brevity and not looking up all that stuff and tasking us with correcting for the activity, we're not going to bother. Okay, so part B then says if we have a solution containing 0.8 moles per liter of F minus, concentration of the tin, and thus the number of moles of that stannous fluoride that can dissolve, we can essentially set up an algebraic equation for that. And that's going to come from, again, the K of the solubility. Could use activity here, of course. Here's our equation, and now we need to substitute. So we have the K, and what we need to do is substitute in a way that we can solve one for the other. So we already know we know the concentration of fluoride. That was set at 0.8 moles per liter. So essentially what this would look like would be the 2 plus concentration times, well, excuse me, we actually don't know exactly the fluoride concentration because it can change if the stannous fluoride dissolves a bit, right? So it could change a little bit, probably not much. But let's go ahead and write this out. Let me say, before we do that, we can substitute one for the other because we know that 1 mole SNF2 is going to yield us 2 F minus and 1 SN2 plus. So we can make a relationship between F minus and SN2 plus, which would be for every F minus we have, that should be, let's see, 2 times the tin concentration. Okay, so we can then substitute in place, and now this is where we're adding stuff. So we can make a substitution here and say, essentially, we can put, instead of the Sn here, we can put F divided by 2. And actually, I'm going to do this a little backwards. I'm going to put what I'm considering here is they made a substitution for it, and they just used S. And I'm trying to think, did they use F or did they use the Sn to get there? We're going to get there algebraically one way or the other by the substitution. I guess maybe they used the... Let's see. I think it's F that they're using because that's where the 0.8 is coming through. So we're going to substitute for F and say this is did I do this part right? Help me check this logic here. So for every time we dissolve one of these molecules, we end up with 2 F minus. That means the F minus is going to be twice the concentration of the other. Yeah. Okay, so then that should be, if we say F minus is S, what I'm aiming to do is get at the equation they had there. So we could say this would be Sn2 plus times S squared. We could also then substitute and say this is going to be S divided by 2. Did I do that right? Times S squared. There is at least one small mistake here, and I might have more than that. Because what we need for the F minus, when we put that in, that has to be the 0.8 plus whatever dissolves. So I'm doing something a little bit off here. And I encourage you to find my mistake and correct me here. I'm going to back up a little bit to here and say F minus should be equal to whatever dissolves plus that 0.8, right? So so we need to find, I guess, that portion that is going to dissolve, and maybe that's what the S is here. That would make sense, because if S is that solubility, that would be the moles per liter of the stannous fluoride that dissolved. And then that would make sense. So let's define S a little different then. So if we define it that way, then every 1 mole of the SnF2 gives us the 2F minus and the 1 SN2 plus. And we could write, let's see, how can we put that into the equation form? Okay, might not get the explanation fully, but let's just track right here and say, in this case, we're going to call Sn is S, and F minus that is dissolved is 2S. And if we do that, which could make sense then in our equation here, we'll say K is going to be equal to the amount that's dissolved plus the 0.8 when we're calculating the F part of that equation. So instead of F minus here, we're going to put in 2S plus the 0.8 moles per liter. That term will get squared, and we also have the S from the zinc. Okay? I think that's how we're going to get to this equation here. Does that make sense? Okay. All right. Apologize for my lack of clarity on that. Okay. So with that, we are left with a scenario where we have a cubic equation because we have S cubed in this. And it's not super convenient. However, if we think about the concentration of S is the amount of this stannous fluoride that's dissolving. In the first part, we said that, well, there's about 10 to the minus fourth moles of this stuff dissolving per liter. And when we add all this fluoride, it should be less than that. So if we think that S is at most something like 10 to the minus fourth, then the comparison of 2S to 0.8 is quite small. So it's a rounding error of at least the fourth decimal place, right? To add that 2S to the 0.8 would be like 0.80001 or something like that. So in that case, 2S should be a lot smaller than 0.8, even if this addition of the NaF made no difference. So given that, we can actually simplify it quite a bit and say this is kind of like S times 0.8 squared, because that's approximately 0, relatively. Okay, so that's the next step here that the book explains. We solve for S, and of course, if I had just looked ahead a little, we could have clarified that a little easier. S is the amount that dissolves. Where did my cursor go? Okay. And it's noting that we can assume that 2S is a lot smaller than 0.8, so that gives us these values. Okay, so at the end of the day, the amount that dissolves is 2.81 times 10 to the minus 9 moles per liter. Comparing that to what dissolved when there wasn't any NaF in solution, we were at 10 to the minus fourth or fifth. This is quite a big difference, right? So that's the common ion effect in practice. Okay. Apart from my muddling my way through that, does that make some sense? Okay, so I wanted to cover a few other kind of notable chemicals in solubility and precipitation reactions. So a couple before we get to kind of the carbonate and hardness, softening sort of systems. Wanted to cover hydrogen sulfide. Got a nice little video on the hazards of hydrogen sulfide. So we probably all recognize this as that rotten egg smell. Or if you've never had a chance to smell a rotten egg, hopefully maybe you haven't, you've surely smelled hydrogen sulfide from other rotting or decaying organic matter. Sulfide is an important component of all biological matter because it's part of DNA, part of proteins, things like that. It's not in a huge quantity, but it's there. And so if you have sulfur and an anaerobic process, a biological process decomposing stuff, you're going to end up having bacteria that use the sulfate as a source of oxygen or an oxidizer, and that's going to generate hydrogen sulfide, H2S. Sometimes that'll be, there's an equilibrium reaction with HS minus, as you probably know. Technically you can get to S2 minus, but that's not really realistic in typical aqueous systems. The pKa is like minus 17 or something like that. So we don't actually achieve S2 minus in most systems. So we get hydrogen sulfide in a lot of biological and geological processes. Some mineral systems, the geothermal vents might actually spew hydrogen sulfide. That's probably the primary risk of being too close to an active volcano that's discharging that kind of stuff, is the gases can be quite noxious. So hydrogen sulfide, our noses are actually quite sensitive to it, and we smell it way before it's dangerous, but it is quite dangerous. So if you smell it, you will have a visceral reaction, right? And that's probably, you know, if we think from an evolutionary lens, that has probably protected lots of people from eating something they shouldn't, whether or not they knew about bacteria. So it's very helpful to be sensitive to it. Part of the reason it's so hazardous is because of its propensity to complex with things. So it tends to be highly insoluble when complex with soft metals like copper 1+, silver+, cadmium 2+, platinum 2+, gold+, and mercury 2+. And part of the reason why these heavy metals are toxic is because they tend to complex with sulfur that's doing something else in our biology, right? And so if the sulfur was supposed to be helping in some other way or participating as part of a protein or something, and suddenly one of these heavy metals comes along and attaches to it, suddenly you've just ruined the function of that biological molecule. So that's part of the reason. It also can be important for binding with some other things: chromium 2+, manganese 2+, ferrous, iron, cobalt, nickel, copper 2+, and zinc 2+. So lots of interesting things there. Also have a little video we can take a look at. This is some safety talk video. I don't remember what. They're making it sound really exciting.
Hydrogen sulfide is considered a broad-spectrum poison. It can poison several different systems in the body, although the central nervous system is mostly affected. The specific mechanism that causes issues in the body is that hydrogen sulfide forms a complex bond with iron and mitochondrial cytochrome enzymes, thereby blocking oxygen from binding and stopping cellular respiration. In simple terms, your cells cannot oxygenate and quickly die, resulting in the shutdown of the vital organs in your body. The body is capable of detoxifying low levels of hydrogen sulfide in the body through oxidation to a harmless sulfate molecule. However, at a certain threshold level, the cells cannot oxygenate the hydrogen sulfide and are overwhelmed. This threshold level is considered to be in the range of 300 to 350 parts per million, or ppm. Exposure to short-term, low-level concentrations can result in symptoms such as eye irritation, shortness of breath, sore throat, coughing, and possibly fluid in the lungs. These symptoms usually go away in a few weeks. Long-term low-concentration exposure may cause loss of appetite, fatigue, headaches, irritability, memory loss, and dizziness. The exposure limits for hydrogen sulfide vary among jurisdictions and industry activities. The most widely recognized standards for an 8-hour time-weighted average, or TWA, is 1 part per million and a 15-minute short-term exposure limit, or STEL, of no more than 5 ppm is recommended by the American Conference of Governmental Industrial Hygienists, or ACGIH. Hydrogen sulfide concentrations above 100 parts per million should be considered immediately dangerous to life and health, or IDLH. Let's review the hydrogen sulfide levels at which different symptoms and effects are observed. To start, an extremely low recognition threshold of 0.0047 parts per million is recognized as the odor at which 50% of the population can detect the characteristic rotten egg odor of hydrogen sulfide. The odor becomes more offensive at 3 to 5 parts per million. With prolonged exposure at 2 to 5 parts per million, nausea, tearing of the eyes, headaches, or loss of sleep may occur. At 20 parts per million, symptoms may include fatigue, loss of appetite, headache, irritability, poor memory, and dizziness. At above 30 parts per million, the odor is described as sweet or sickeningly sweet. Exposure to 50 to 100 parts per million leads to light conjunctivitis and respiratory tract irritation after 1 hour. This level of exposure may also cause digestive upset and loss of appetite. At 100 parts per million, the olfactory nerve is fatigued after 2 to 15 minutes of exposure, resulting in a loss of smell. Additional symptoms, such as coughing, eye irritation, altered breathing, and drowsiness may occur after 15 to 30 minutes of exposure. Throat irritation can occur after 1 hour of exposure. Death may occur after 48 hours. At 100 to 150 parts per million, the loss of smell occurs immediately. At 200 to 300 parts per million, exposure leads to marked conjunctivitis and respiratory tract irritation after 1 hour. Pulmonary edema may occur from prolonged exposure. At 500 to 700 parts per million, exposure will cause staggering and collapse within 5 minutes, serious damage to the eyes within 30 minutes, and death within 30 to 60 minutes. Hydrogen sulfide concentrations greater than 700 to 1,000 parts per million can result in rapid unconsciousness, knockdown, or immediate collapse within 1 to 2 breaths, resulting in death within minutes. At 1,000 parts per million, a single breath results in immediate loss of consciousness, followed by cardiac arrest. An important point must be noted here. A concentration of 800 parts per million is the lethal level for 50% of humans with 5 minutes of exposure. Research has shown that symptoms of hydrogen sulfide exposure vary considerably because of individual physiological makeup. Studies have indicated that persons previously exposed to hydrogen sulfide tend to be hypersusceptible to further exposure rather than building up a tolerance to it.
Okay, so it almost sounds like some sort of advertisement there for the benefits of, or the detriments rather, of hydrogen sulfide exposure. And by the way, if I wasn't clear, H2S will often come off as a gas. So of course you can have some dissolved, but H2S would be gas in equilibrium with the liquid phase. So the pKa between there, I think, is somewhere around 8 to 9 range. So if you are working with hydrogen sulfide, you essentially, if you want to keep it basic in order so it's not off-gassing if you have to deal with it in an open situation. Thankfully, it is quite smelly, so we tend to be pretty aware of it if there is some sort of risk. That's probably enough to scare you on in terms of like, let's be careful with that. There's a neat article here, also has a description of the history and kind of the person that first kind of showed a way to produce hydrogen sulfides. Actually, I think it was some musician that was also kind of a chemist by hobbyist. So if you're interested, there's some some neat info there about the history, and a few minute audio clip here about that as well. Okay, so hydrogen sulfide then, kind of in a nutshell, quite important for several solubility things, in part because it binds so strongly with different metals, and a lot of times they will be rather insoluble upon binding. So that ability to bind with stuff, again, that's why it can bind with iron in our system to cause trouble with oxidation reactions, things like that. Okay, next step would be phosphates. Phosphates are another one that is quite important for both biological and natural systems. And we often talk about corrosion control, and you'll see this a lot with the Flint water crisis and kind of water distribution system things. We will often say orthophosphate. And say that's our corrosion control. That is the form of PO4 3-. So if we are adding orthophosphate to a system, maybe it's like Na3PO4 or something, so it will dissolve as that orthophosphate form. If you were to do that, we recognize, kind of like the carbonate system where we have the different values of it, the orthophosphate would exist at high pHs, right? So adding it would essentially be adding something that's ready to take up some protons. So it should, if you add it in that kind of form, it'll probably end up at sort of a near neutral pH. You'll end up with H2PO4- and maybe HPO4 2-, some combination of those at near neutral pHs. That depends on the exact pKa, and I don't have those off the top of my head. But if you're adding as orthophosphate, that's going to scavenge up some of the acidity that's in there, and it's going to help buffer the system to keep it in that slightly elevated pH, which in general helps keep the minerals and metals in your system less soluble, so that keeps them on the pipes. Now, one thing to note about phosphate, and one thing we can recognize about different minerals in general and different ions, most of the +1 charged ions are typically quite soluble. If you have like sodium and a chloride, +1+1, that tends to be quite soluble because there's not a whole lot of charge density drawing them together, right? If we're talking about something like a salt or a similar mineral. So if we get something that has a higher charge density with the +2s, -2s, and 3s, they tend to have much lower solubility. There's a few exceptions, but something like calcium sulfate, CaSO4, or gypsum, tends to be rather insoluble. And that's because there's just a dense charge here and a dense charge there that are acting to keep that from coming apart. So phosphate then is going to be pretty good at that. When it binds with something, it's going to bind pretty strongly. And so most phosphate metal minerals then are quite insoluble. So we'll see several of them. Hydroxyapatite is one of the most common ones. We'll even talk about enamel containing some apatite on your teeth, things like that. And so hydroxyapatite here is calcium 5 with PO4, three PO4s, and OH as a solid. So hydroxyapatite then, we could describe its solubility and everything, and that's a common precipitate if you had a lot of calcium and phosphate in a solution. Now, given that phosphate tends to be, pretty insoluble when paired with stuff like that, it's actually not found too high concentrations in nature, in natural systems. Now, if we have a contamination like a discharge of wastewater that's got a lot of biological materials, that could add a lot. And in consequence, a lot of stuff in nature would be sensitive, a lot of microbes would be ready to start growing if only they had some more phosphate, for example. So that's one of the components that could be a limiting nutrient. Now, it's not a guarantee that phosphate is the nutrient, but in many cases there's a concern that it would be the limiting nutrient, and at the amounts we would discharge in a wastewater system, it could be a problem. So typically we see less than 1 milligram per liter as phosphorus, or that would equate to less than 3 milligrams per liter as phosphate in natural systems. So many of our wastewater discharge regulations are about at 1 milligram per liter as a limit. Okay, so there's a hydroxyapatite mineral there as well. We can take a look at the solubility diagram for hydroxyapatite and kind of take a look. There's actually a couple types of phosphates that might be important, so we'll look at a couple of them here. And we can see in general, we can look at the total calcium, the total phosphorus, and they are matching up nicely because if you have enough of both of them in a system, they're going to precipitate as that hydroxyapatite. You can see that as we increase in pH, the solubility is decreasing, so more of our system would be the solid form. So it might not be clear, but in this diagram we're saying that everything kind of above these lines, that's the solid form, and to dissolve it you could move the pH down and more of the solution would be in the dissolved phase. So a good way to look at it would be, these are the dissolved things on the lower left side, and then anything up above that edge there is a solid. So we could take a look at that and the different speciation that would be there. Just wanted to give you a general impression on what that would look like. Okay, the other important phosphate mineral would be fluoroapatites. And this one is calcium again, so calcium, phosphate, and fluoride instead of the OH minus, or so the OH group. So fairly similar, can plot these two on a similar diagram. So if you have some F minus in your system, that could also yield some fluoroapatites. Might dominate a little bit at high pHs comparatively. Just another important mineral in natural systems. Okay, the last one that I want to talk about for phosphates would be struvite. So this one is a magnesium ammonium mineral, so magnesium, ammonium, and phosphate. So MgNH4PO4 with 6 waters. So struvite, this is a mineral that can form and can be a big problem in wastewater. So if you have wastewater containing a lot of magnesium, which is not always the case, I mean, a lot of our natural systems have it, so if you have hard water and everybody's flushing that water down the drains, then maybe you have a lot of magnesium. But otherwise, it can be the limiting component for struvite formation. But if it's not limiting, you have some serious problems potentially with the formation of struvite within the pipes in wastewater treatment systems because, and even on like impellers and things like that, because we have typically lots of phosphate and lots of ammonia, right? So given that this is a rather insoluble, I mean, it's not crazy insoluble, but it's prone to precipitate, it causes big problems. And here's an image showing some of those, some pipes from a wastewater system. So that can be a big challenge, but it's also a potentially really good benefit if we can control it on purpose. So one of the books was mentioning we can use struvite as a fertilizer because the ammonia and phosphate are great for plant growth and things. Perhaps we wouldn't want to use 100% struvite for a fertilizer because we typically want a ratio that's got the right amount of phosphate compared to ammonia or nitrogen. And usually I don't think that's going to be 1-to-1. So maybe you'd mix this with something else, but certainly it could be a good fertilizer. So there's a possibility of adding magnesium to wastewater in a controlled fashion to promote struvite formation, which would actually strip the phosphate and a lot of the nitrogen out of your wastewater system, which would be really beneficial. So this was highlighted by one of the books as like, and I don't know if this is performed much in practice or what the typical challenges might be, but it really would solve quite a lot of the typical challenges, which would be the nutrient control. So tertiary treatment would often target biological processes that could do this, get rid of the excess ammonia, so nitrogen removal, and get rid of phosphate as much as possible. But neither of those gives you a product that is directly usable for like a value-added kind of product, right? You can digest sludge and generate some methane and maybe digest the biosolids and create some fertilizer that way. So maybe you can get there, but this is a little bit more direct. So if you could just precipitate it on purpose, it's a pretty neat concept. So might be room for some chemistry to get involved with wastewater treatment in that regard. Okay, next up would be the carbonates, and well, one more note about the phosphates. I mentioned, but in drinking water distribution systems, we don't typically have a lot of ammonia, right? So we're not really going to be producing struvite in our water distribution systems, but we do actually want a slight precipitation of any mineral rather than a dissolution of minerals. So one of the reasons why we have corrosion control, especially in the form of the orthophosphate, is to promote a generically constricting pipe instead of a generically dissolving pipe. Because if you imagine over very long time scales, you're generally going to be doing one or the other. Your equilibrium is going to be balanced one way or the other. So with thousands and thousands of liters of water flowing through every day, you want to have a slight accumulation of minerals rather than a slight depletion of minerals, metals or whatever. That means, for a drinking water system, that's important because if you ever have the system dissolve, then you could have your water's going to leak. You could have contamination coming in from the outside. And if you had any lead in the pipes that were put in there a long time ago, or in the soldering joints or anything like that, then you're leaching the lead right out into the water, right? So that's all sorts of reasons why we would promote mineralization in the drinking water systems, but just a little bit. So, replacing them after 100 years, that makes a lot more sense than letting them corrode. Okay, so next up, carbonates. Now we've talked a lot about carbonate already, and we know that it can be CO2 essentially dissolving and have some equilibrium reactions in that regard, and carbonate, bicarbonate, carbonic acid, all of that. But in natural systems, we can kind of take a look at the different carbonate and calcium precipitates in particular. So, well, we've got calcium, magnesium, both making carbonate minerals. So we're going to take a look at those a little more closely. So each of those three are rather abundant in natural systems, especially calcium. Magnesium is often there, just a little less amount. And we have several crystalline forms, so solid forms of calcium that we can consider. Calcite is the most thermodynamically favored, it's most common, and most marine planktons, any of them that are going to form a calcium carbonate. Some diatoms do silicates instead, kind of as a structure or shell. But a lot of planktons will have little calcium carbonate shells. These are going to be in the calcite form, and essentially these are largely what generates the mineral, the calcium carbonate, that will end up forming limestones. So over geologic timescales, you get a lot of these calcium carbonates formed, sedimenting out of the ocean once they've died and all that, forming layers and layers of sediment, over geologic timescales that can be compacted and processed, so to speak, and that yields limestone, which is mostly this calcium carbonate. Okay, another form would be aragonite. That is the type of crystal that a lot of mollusks and clams, oysters, things like that will form, also a calcium carbonate. So if you ever were to take, you can take limestone, you can take a shell like this and add some acid to it, and it should start fizzling because you're going to be dissolving that and releasing the carbon dioxide, right? So you should be able to kind of test different minerals to see if they are a carbonate species like that. Vaterite is another one. Didn't read much interesting about that. Now, most of the ocean is super saturated with respect to calcite, at least in the upper regions, but below about 1,000 meters, it's then undersaturated. So if you have diatoms composed or plankton composed of calcite in the upper oceans, they're going to be easily forming these shells, precipitation reaction encouraged by the microbes. But if then they fall far enough, you might have a situation where they're dissolving back because now you're undersaturated. So a lot of that oceanic kind of stuff will depend on what's going on there. And then the deep ocean there, we could think about why that is. And I'm actually not exactly sure. It could be a difference in the calcium concentration. Probably more likely it has to do with the dissolved carbon dioxide, so the carbonate concentration. There's probably less of it lower in the oceans, meaning it's less likely to push it that way. It could also simply be that the equilibrium constant changes a bit with the pressure and temperature changes. It's also a plausible reason. But in general, it's under the saturation level for calcite, whereas upper ocean calcite forms readily. Okay, so let's build a calcium or a calcite, solubility diagram. So we've done a little bit of this type of stuff, and so this exercise should look pretty familiar. And I'm just going to walk us through it to kind of see what would it look like to set up a diagram that's going to show us at what level do we have that transition from solid phase to dissolved, right, across different pHs. So we're going to do, just like we looked at that, this graphs with the phosphate, we're just going to develop a simple one. So I'm going to kind of derive with you the different pieces. Well, first of all, we know our carbonate system has two Kas, right? H2CO3, we could put the little star if we want, in equilibrium with H and HCO3 minus and CO3 2 minus, right? So each of these in equilibrium. And we get the two Kas, right? This is familiar. This is H plus times HCO3 minus over H2CO3. Kas are at 10 to the minus 6.35 and 10 to the minus 10.33. So seen this before. This is the carbonate system. Okay, for calcite, CaCO3 in the calcite form, we have a solubility product of 10 to the minus 8.48. So we can set that equal to the activity of the calcium times the activity of the carbonate. So let's start at one end of the pH or the other, and we'll start at the very basic side of it. So we're just going to say under one particular condition, and we're going to start with a closed system, by the way, so we're not worried about gas exchange, so this would be a little deeper in the ocean where we're not right at the surface. So we have a closed system and a high pH. So if we took a pH above 10.33, we are above that second Ka. That means we can simplify to say the majority of the total carbonate is in this carbonate form. Okay, so that's going to be an assumption that lets us plot out what does this graph look like under those conditions. So we're going to start kind of drawing our graph, and we're going to start with kind of the high pH area. Okay, so we can take, with that assumption, we can say that the calcium should be, we'll just rearrange our solubility product, would be equal to that product divided by the carbonate. We can take the log of both sides, and we'll do this to get it in more of a linear, plottable fashion, because we can then plot the log concentration here as the y-axis. And that just becomes really convenient as we deal with this, because taking the log on the right, that gives us log K minus log C, or log of the carbonate in that case. So now we have a function of calcium in terms of the carbonate concentration, which is pretty handy. And if we know, so we can select maybe some typical carbonate concentration. If we know that, then we have an equation that says, well, the log C, in this case we're going to do log calcium, right? We want to know at what level, or where is that level where it would be at equilibrium with a solid, right? So given that, we can write this equation here that says, the log concentration is going to be equal to, and we're going to assume 1 millimolar of the carbonate. So we're just going to put in 10 to the minus 3 here, right? Because that would be this log K minus the log carbonate. We made the assumption that all of the carbonate is in the carbonate form. That gives us an answer to say, if this is a log plot over here, going from 0 down to, I don't know, -10 or something, then we could say, all right, at least for the values that are above 10, 10.33, we know that this value should be at -5.48. So it should look something like that. At all those pHs above 10.33, we have a log C of -5.48. Okay, does that make sense? Kind of how we got there? Okay, so then we can do the same process, but select the next segment. And we might have a slightly bent transition there or something, but we can probably find another straight line like this, maybe with a slope, that can guide us to say, okay, well, at the next range, we're going to go, we're going to have a different function for that. So let's take the area between the two pKa's, right? So pKa1 at 6.35 and pKa2 at 10.33. We're going to assess the range there. So in our little pH PC diagram, we're now looking at the range, we'll say, kind of that segment of it. Okay, at this range, the bicarbonate predominates for the carbonate species. So now we're going to solve our system in terms, with that in mind. So we've got our calcite dissolution here again. We know our Ka's. This time what we're going to do is we're going to relate the carbonate to bicarbonate. So because the precipitation reaction correlates to the carbonate, we need to get this in a function of carbonate, and we can do that by combining two equations. Now normally we write the bicarbonate equilibrium equation like this. Right? That's the normal way we do it. We can flip it and invert the K. So 1 over K would be the same thing as flipping that and solving for a new K. So convention is to write this is K A 2. So 1 over Ka2 would be just swapping those backwards. Okay, so that's what the book is doing here, and saying we're going to take 1 over Ka2 and write this in reverse so that we can add these two equations together, which what we'll see is the carbonates will cancel, and we'll have a function of the bicarbonate. Okay, and that means we can multiply then the 1 over Ka2 times the solubility product. When we add those two equations together, we multiply the constants together, right? So then rewriting all of that, we have the calcite plus H plus is in equilibrium with calcium plus the bicarbonate. And the this new K value here, I think this is K solubility 1, Ks1. By multiplying these two together, we get 10 to the 1.85. So this would be K solubility times 1 over Ka2. Okay, with that, we can do as we did last time and get a function of the calcium. We can get calcium as a function of the bicarbonate in this case, and therefore the pH. So we get this Ks1 equal to calcium times bicarbonate divided by H plus. We would also have the calcite, but that goes to 1, right? So the calcite, it's a solid, so we treat it as 1. So that gives us this function, calcium. If we rearrange, calcium equals the Ks1 times H plus divided by bicarbonate, and we could take the log of that, get a log calcium is equal to log Ka1 plus, Ks1, plus log of H, which is our pH, and minus log of the bicarbonate. So again, recognizing that we have some assumption of the total amount of carbonate, Ct, we can put that in right here at this pH. Okay, so and the log H plus, that's like a negative pH, so that goes here. So ultimately our equation becomes log calcium is equal to 4.85 minus pH. Okay, so very handy. This is now a function of pH, so it will be a slanted line between those two values. And if we were to plug in the pH of 10.33, we should find the same value that we had last time at right here, which was negative 5.48. So let's go back forward and say 4.85 minus 10.33, yeah, that should be minus 5 point something, right? So that actually meets the line nicely. So I think we already did something like this, so this should then be something like that. Okay, last piece, we're going to do that same process. Now we're going to take the lower pHs, anything below pKa1. Same process, same type of stuff here. Here we have the same thing we derived a moment ago, this calcite in equilibrium with bicarbonate. So this was from the previous slide. Going to do the same reversal and addition such that the bicarbonates will cancel, and this is going to be 1 over Ka1 times that Ks1 we derived will give us this value, Ks2. Go through the same process, derive an equation for how the log Ca changes as a function of what's in there. And again, assuming that we've got 1 millimolar, that's going to be the total carbonate here. We end up with an equation that says our log for calcium is equal to log of 10 to the 8.2 minus this log of the total concentration minus 2 times the pH. Putting all that together, we end up with an equation 11.2 minus 2 times the pH. So at this point, we have a twice the slope as what we had before. So if it looked something like this, now we're going to slope even stronger. Okay, does that make sense? All right, so here's the plot, and it turns out that what I kind of drafted with my little drawings was not too far off. Again, we can kind of think of this as here's the dissolved species, and we didn't put all the speciation diagram on here. We're just looking at the values at equilibrium with a solid, so at saturation, and then anything at or beyond that, we have a solid form of calcite. So that's kind of the simplified way, or I guess the direct way to generate a solubility diagram. And it's none of that stuff that you haven't seen before, but I just wanted to put these pieces together a little bit, kind of show you how we could get at those equations. And this is also the type of thing that the MinTech software would do and can do for many different species. Now that's all for the closed system. We can look briefly at what happens in an open system. And it turns out in this sense, it's a little simpler. And that's because the CT changes. So, and CT will change with pH. So we could go back and look through our notes and find that we can have a carbonate concentration, CO3 2-, as a function of the different Ka values and the function of the partial pressure of CO2. So given some partial pressure, also a function of pH, we can then put in this equation and find the carbonate at any pH. Right? There's several constants in here, including the constant for water. There's the pH squared, or the H plus squared rather. But really that's pretty straightforward. We can put that in and solve our problem for carbonate. Now, calcium then is in equilibrium with carbonate. Like that was kind of where we started with, right? All the way back here, we had the calcite in equilibrium with carbonate, right? That's sort of our starting point. So given that, if we can solve for our carbonate at any pH, given the open system, then it becomes a little simpler because we don't have this angular change in what's happening. We just have the carbonate changing, therefore the calcium carbonate changing. So our solubility then looks like this, where we have solid here and dissolved species here. And you will notice that this curve is pretty close. This one dips down to a lower pH, but it's fairly close to this in terms of where it starts becoming a solid. And if we put all these pieces together, the line here will be described as this log of Ca2+ is equal to 13.2 minus 2 pH. That's ultimately what we derive if we put all those pieces in and solve. Okay, does that make sense? All right. Another notable mineral that we could talk about is dolomite. It's kind of an interesting one. This is calcium magnesium carbonate, CaMg with 2 CO3s. Historically, this was pretty difficult to synthesize or to cause it to precipitate under normal conditions. Apparently there was some history here where people were trying. They really only found it generating at low temperature. The book says low pressure, but I don't think that meant that. Maybe that was deep, so high pressure, or I'm not sure. Low temperature hypersaline lakes. Also, people noted that if there was sulfide around, that really limited the formation. So it was a little surprising that when researchers found that sulfate-reducing bacteria actually induce the dolomite formation. There's a little confusion there until somebody did kind of a smart experiment, realizing that if you change the pH across the saturation boundary for these minerals, you end up kind of oscillating and forming this this dolomite. And part of the issue here is because it would be very easy to form calcite or the magnesium carbonate just by itself, that solid. So trying to get them both together at the same time was kind of interesting. The one common place this is very prevalent is the Floridan aquifer. Most of Florida, lots of southern Georgia, South Carolina, Alabama, even a bit of Mississippi, close even to where we are. Massive aquifer system here, and a lot of that is this dolomite limestone. So I was talking about kind of the source of lime in general, or limestone in general. Well, this could be the outcome of lots of precipitation in an ocean, going through some geological processes, and ultimately getting primarily dolomite. So has some implications, and if you know much about the geology of limestone, you can tend to have big gaps and open dissolved spaces. So lots of the area under Florida has that kind of that sort of underground topography, which is not the right word, but that sort of geology underpins a lot of that aquifer. Okay, I think I want to save. Well, I'll touch on water softening, but we'll just spend maybe 5 minutes because I need to go get my exams ready for the next class. And I want to solve an example with water softening as well, and I won't have time for that. So just a quick kind of introduction to why we care about water softening and what's up with hard water. Probably heard about it, probably talked a little bit about it already, but the presence of calcium and magnesium, these are divalent cations. Actually, other divalent cations would be included as well in terms of what's important for hardness, but these are the primary ones. We label them as hard water, I guess because it ends up creating mineral deposits if you're using it, and so there's a hard aspect to it or something is maybe a good way to describe it. It causes soap to have trouble forming suds because these soap molecules will essentially be wrapped around pretty strongly these highly charged molecules. So that charge kind of crumples the soap molecules so that they're not causing the same reduction in surface tension of the water that you intended. So you just end up needing to use a lot more soap per volume than you wanted, or you would normally use. So if you ever visited somewhere where like the soap just didn't form suds and there was like mineral deposits and scaling everywhere, that's kind of the thing. In reverse, if you have really, really soft water, it kind of feels like it's impossible to get soap off because you just have that layer of water, and even just water can feel a little soapy because of that. Turns out that EDTA, we talked about that with calcium already, it's added to a lot of shampoos. I didn't know that, but apparently that's a thing so that you don't get calcium depositing in your hair, and it's easy to get the calcium out, and calcium's not going to then ruin the soapy effect of your shampoo. Okay, so how do we soften water? Well, we can use ion exchange. We're going to swap sodium for the calcium and magnesium. Of course, that's going to add a fair bit of sodium. That's probably not a problem, maybe a tiny concern. Really, probably not a realistic concern for the amounts that would be there. And then you can regenerate those resins. A little closer to what we're going to talk about is manipulation of solubility using lime, soda, and ash, meaning pH adjustments using carbonate added on purpose, or maybe getting rid of it, and the ash is a sodium bicarbonate. So altogether, we're manipulating that Le Chatelier's principle. When are we causing precipitation? What are we doing with that? So there's it's kind of a back and forth process to induce precipitation of different stuff. Okay, where do we care about hardness? Any of you lived in one of these red areas or visited? Okay, I haven't really gone to anywhere super hard water. So just as a reference point, I grew up kind of in this area. Then I lived for a couple years right around here. So there was some hard water around, but I don't think it was in the worst of it. And of course, now we are kind of in this region. So if you kind of look at different places where you might visit, you might find, this water feels weird. Taking a shower is strange here, right? I also grew up visiting relatives in Florida, so I think I probably saw some water or felt the water being a bit different down there. If we take a look at what describes hard water, we tend to describe it milligrams per liter as CaCO3, as calcium carbonate, right? The amount of hardness described that way is kind of describing how much of this precipitate we could form if we were to precipitate it. We have different values here, thresholds. We could put it in sort of a charge equivalent, milliequivalents per liter, or as this milligrams per liter of calcium carbonate. So typically, soft water is about less than 50 milligrams per liter CaCO3. Water softening using the lime soda ash thing can only get you down to about 30 or so hardness. So you can get soft water, just can't get ultra soft. And so there's some thresholds there. All right. We will embark on a bit of water softening probably next time and try to get through the precipitation stuff that I want to talk about and onto redox chemistry. All right, I'll see you guys. So not Thursday, no in-person class